All right, so let's begin, and we will start slowly, and then we will pace up. Uh, so today we are going to discuss week 12. In week 12, we are going to see another country in the world of mathematics, right? Which is ordinary differential equations, and we wanted you to get used to this concept because all the circuits that you are going to learn right now you might be learning and which you might be seeing in future. Mostly they are all governed by some differential equation. And once you find the solution to that differential equation, then that solution can be the voltage across the circuit, across the resistor or capacitor or whatever the component we are interested in at a particular time. Or it may be current passing through the circuit and many other examples, right? So for that, when these circuits are governed by differential equations, you should know how to solve those differential equations, and that is what we are going to teach you in this particular week. And in week 12, since this is the very first time that you are seeing ordinary differential equations, so we'll not be going through the advanced or maybe higher order ODE, not even non-linear ODEs. Rather, we will be showcasing or discussing very basic first order homogeneous ordinary differential equations, and then little bit of second order, and all the differential equations that we are going to discuss in week 12 are linear. I will also tell you what linear is and all. And I hope most of you have started watching week 12. If not, then please do start, because week 12 also has lot of concepts to be studied, and we don't have enough time. Okay, so you should really start looking into week 12 concepts. Okay, so let's begin. As I said, week 12 is all about differential equations, mostly ordinary differential equations, and yeah, linear ODEs. Which I will start with what is a differential equation, and then we'll see what is the first order differential equation. What does it mean by second order? What is this order? So we'll discuss all those things. Okay, so let's start with the very basic definition of what differential equation is. So any equation, since it is an equation, it will be in the form of equation. So any equation that involves a function f and its derivatives, maybe f prime, f double prime, f triple prime, all the higher order derivatives. Okay, and some other functions of x, may not be f, some other functions of x. And overall, an equation is formed using all these things. And since it is an equation, it should be satisfied with some applicable values of x, right? So an equation, once we have an equation, we'll solve the equation, right? So which we have seen right from the beginning, right? So when you have a quadratic equation, we try to solve that quadratic equation for x, right? If it is a polynomial equation or any other equation, we will try to solve it for a certain value. So here differential equation also will try to solve the equation to find the function f. Okay. So again, do I have to if I have to repeat it in a proper way, this is how the definition goes. So suppose f is a function of x, we have a function f, and the differential equation is an equation first, which involves the function itself and its derivatives. So it can be starting from first order derivative to nth order derivative, and can be very large also. It doesn't matter. And some other functions of x, which needs to be satisfied for all applicable values of x. Such an equation is called a differential equation. And you can see there are some examples here. Right, so the very first example is f prime of x is equals to x. So this equation has the first derivative of x and some constant. Right, overall it forms an equation f prime of x minus 4 is equals to 0. Right, so we will try to solve that equation and try to get f of x. So here, once the equation differential equation is given to us, we will try to find the function, right, by solving the differential equation. So for that, we are trying to understand what a differential equation is. So even the second example has f prime of x, right, and then we have f of x and then a constant, right. So this equation involves the first derivative of the function f of x and the function itself and a constant, right. So it forms an equation. This equation is also a differential equation. Similarly, in the third example, there is double derivative of the function, and then we have first derivative, and then we have the function, and we have some other function of x, right. It's not f of x, it's sin x. Sin x is also another function of x, right. So again, this also forms an equation, and the equation has only the function and its derivatives and some other functions of x. So it doesn't involve any other variables functions or any other new variable, right. So this is a differential equation. And now coming to order. So order is basically tells us the highest derivative that is present in the equation. Okay. So for these examples, you see the first example has only the first derivative, and that is the highest derivative that we have. So therefore, this is a first order ODE. So first, because it has only the first derivative, and that will be the highest derivative. Even in the second example, we have f prime of x and f of x. And if you see f prime of x, which is the first derivative, is the highest derivative. And this will also be first order ODE. And if you see the third example, this has double derivative, first derivative, and f of x. And within the first derivative and the second derivative is the highest derivative. So it's a second order ODE. Right. So order basically captures the highest derivative that is present in the differential equation. That's it. So that's the order. Okay. All right. So these are some differential equations and their examples, and we'll also see some real life examples also. And as mentioned here, differential equations actually govern almost the entire physical world. So you pick any domain, any engineering domain or any domain, you will see a differential equation. Okay, and you belong to any engineering background, you have to learn these differential equations and solving the differential equations. Okay, so we'll see a couple of examples now, and then we'll understand it better. Okay, so let's see the very first example, simple example, which is when an object is just falling from some height to the ground. Okay, so the initial position of this apple is at some height, and it is dropped from that height. And since at the start its speed will be 0, and we will say the position will also be 0, we'll assume that the position is also 0, and it starts falling from there to the ground, right. So after we leave the apple from that height, as time progresses, this apple also moves downwards, and initially the speed may be 0, but slowly it paces up, right. Like when you leave the apple, it will start increasing the speed, and slowly the speed increases because of the weight and the gravity, and also it moves downwards. So the distance will also change, and the speed of the apple will also change with respect to time. So both x of t, which is the distance, position, maybe you can call it as position, and v of t, which is the speed, are functions of time. And the speed and time, speed and distance are related to each other, right? We have seen this in week 8. So when I derivate the distance function, I will get the speed, right? So x prime of t is v of t at any time. Okay, so that is there. And then now how do we form this differential equation? By using the physical laws that we know, right? So when this apple is dropped, it is falling in this direction. So if it is falling in this direction, then there will be a air resistance, right? So when it is falling down, air will try to stop it, right? So there will be some resistance from air in this direction. So it's like upward direction, and speed of the apple is in the downward direction. And when apple has some weight, that weight will act downwards because of the gravity, and that weight is actually mg, right? So you would have studied mass into the gravitational force, which is g, right? So the overall, the forces that are acting on this apple are this, right? So this is one force, and this is air resistance. And then if the speed is v of t, we know force acting on this body will be mass into acceleration, and this acceleration is nothing but derivative of velocity or the speed, right? So this, then the force will be m times v prime of t. And what are the forces that are acting on this? Only the air resistance and this weight. So that force m v prime of t is a combination of these two. And since the object is moving in this direction, this weight will act as positive, and this is in the opposite direction, which will act as a negative. So this overall force mv prime of t will be mg minus k times v of t, right? So that will be this equation, and then we will organize this in a neat, clear way, where we bring this kvt on one side, kvt and v prime of t on one side, and then divide the whole equation by m. We will eventually get v prime of t plus k by m. V of t is equals to g. So we know g, we know k. Given k, g is standard thing, right? So 10 meter per second square. It should be 9.8, but we'll consider it to be 10 meter per second square. G is known to us. K and m are also known to us. We know the air resistance, and we know the weight of mass of the object. So all we left with is solving this ODE, which is first order differential equation. Why it is first order? The highest derivative that is present in this equation is v prime of t, right? So it's a first order, and then we have v of t also in the equation, and then we have some constants, right? And there is an initial condition also that we are going to use, which is when time 0, the speed of the object is 0, right? So there is no speed when time is 0. So we have this information also to us. So we'll use this information along with this differential equation. We will solve this differential equation, and the solution of this differential equation is nothing but the speed, which is v of t. So we are trying to solve for v of t, which is the function, actual function. So that is what I said, right? So when we try to solve a differential equation, the solution of the differential equation is nothing but a function. So here the function is the speed. Okay. Any doubts here? right? So all we done was the differential equation will not be given to us directly, rather we should form the differential equation. Okay. So within the same lines now, if it is falling object, this is how the equation will be. What if it is thrown upwards? Any thoughts? How will the differential equation look?
Sign change हो जाएगा ना.
Sorry, it will be the same, is it? So you have a ball, let's say, and you are throwing upwards. So now V of t acts in this direction. Right, so ball is moving in this direction. Now in which direction air resistance will be?
In the opposite direction.
In the opposite direction. So in this direction, and kVt will be in this direction. And in which direction the weight of the ball will act?
Downward.
Downward.
Downward. Weight will also act downward, which is mg. So these are the only two forces that are acting on the ball. And since the object is moving in this direction, ma, which is mv prime of t, should be equals to, here the forces, both forces are acting opposite direction.
It will be negative
Yeah.
of
So
mg
minus mg
minus mg minus
minus
30
kv
of
of t. Right. And if we simplify this or write this in a nicer way, we'll have mv prime of t plus kv of t is equals to minus mg. And then if you divide the whole equation by m, we'll have v prime of t plus k by m v of t is equals to minus g. Right? Any difference? So what is the difference? Is there any difference or no difference? You see, we here the equation is v prime of t plus k by m v of t is equals to g. Here it will be minus g. So that's the difference. Okay, so like this, given the situation to us, we can form the differential equation. Once you form the differential equation, that should be your first step actually. So form the differential equation and then try to solve it. Okay. So if differential equation is given to us directly, then we'll solve it. But if it is not given, rather it is given as some scenario or situation, then we have to find the differential equation from it. Right. So then we will solve. Okay. So there is one more example which is related to our electronic circuits, which is an RC circuit with constant source. Okay, so something like this. So we have a resistor and a capacitor. Resistor with resistance R and capacitor with capacitance C. Inductance C. Okay, sorry, capacitance C. And a constant voltage is being supplied, 5 volts. And when T is equals to 0, the switch is off. At T is equals to 0, we turn on the switch and then current starts flowing in the circuit. Okay, so from Kirchhoff's voltage laws, right? So voltage across the resistor is basically R into I of t, and voltage across the capacitor is Vc of t. I hope those who take ESTCs would have studied this. 1 by C integral I of t dt. Correct?
Yes, sir.
So now if you derivate on both sides using our fundamental theorem of calculus, we'll have V prime of t is equals to 1 by C I of t. So now bring this 1 by c to the left hand side, you will see this equation. So I of t will be equals to c into vc prime of t, and this voltage across resistor will be R into I of t. And since we know the algebraic sum of the voltages should be 0, right? So that's the first equation. So voltage across the resistor plus voltage across the capacitor should be equals to the source voltage, overall source voltage, right? So VR of t plus VC of t is equals to 5 is one equation. And then these two equations are KVL equations. And now what we have to do is we have to somehow use these three and try to get an differential equation with respect to I of t. And then if we solve that differential equation, the solution that we are going to get is current that is passing in the circuit at a particular time, which is I of t. And that will be the solution to the differential equation. And how do we find, or how do we get to this differential equation? We have the first equation, right? So you derivate the equation, right? So in order to get this, so we derivate. So once you derivate, we'll have VR prime of t plus VC prime of t is equals to 0, right? So, and then we derivate this equation because we need V prime VR prime of t. So if we derivate, VR prime of t will be equals to R into I prime of t. So derivating with respect to t, okay. So once we have this, instead of V prime R of t, we will replace it with R I prime of t plus VC prime of t is nothing but 1 by C I of t from the third equation is equals to 0. Then you divide the whole equation by R, we will get this. So I prime of t plus 1 by RC into I of t is equals to 0. And we also have the initial condition. When switch is not turned on, there will not be any current that passes through the circuit, which means I of 0 will be 0. Right, and when we solve this equation, we will get I of t in terms of t and some constants, and which will be the solution to the differential equation. Okay, so this is one more example. And there is also RLC circuit. You can go through it, or later I will bring that example. But these are very easy examples that can be understood very quickly. And then we will be ready to solve the first order linear ODE. RLC involves second order. We'll study that when we talk about the second order. Okay, so far what we have seen is there are differential equations that involves the first order and the function and some constants. Now we will try to look at first order differential equation in general and try to solve it. Okay, so usually the first order linear ODE general form will be, we will have the first derivative and there is some function getting multiplied to the function f of x, and then there will be on the right side you will have q of x. So this will be the general form. But if you have something like b into some f prime of x plus some a into f of x plus is equals to c, you can make it or write it in general form by dividing the whole equation by b, right? Or b of x, even if it is a function also, you divide the whole equation by b of x, then we will have f prime of x plus a of x by b of x, f of x, c of x by b of x. So a of x by b of x is nothing but p of x, and c of x by b of x is nothing but q of x. right? So this will be the general form. F prime of x plus p of x into f of x is equals to q of x, where p of x and q of x will be given to us. All we have to do is to solve for f of x, right? So this will be given. This will also be given. So once we have that, we have to solve for f of x. And that will be the solution for our first order linear. If I just go back for looking at the previous examples, for the falling object with air resistance that we saw, we got the equation like v prime of t plus k by m, v of t is equals to g, right? So if you compare this with general form, you can clearly see that p of t will be k by m, which is getting multiplied to v of t, and q of t, which is on the right side of the equation, will be g, right? So x and t can be interchangeable. They are just variables. Okay, so don't get confused with that. So p of t will be k by m and q of t will be g in that falling object example. Whereas in RC circuit with DC source, we have the equation like I prime of t plus 1 by RC I of t is equals to 0. So here also you can compare it with general form. You can see p of t will be, which is the coefficient for I of t, which is 1 by RC, and q of t is nothing but the right hand side in the equation, which is 0. Right, so once we have this p of t and q of t, it's easier for us to solve this linear ODEs. And since I mentioned this linear many times, there are non-linear ODEs also, where you will see expressions like powers, right? You will have something like functions whole square or derivatives whole square, whole cube. So like this, if you see expressions like this is not linear, right? So this will be not non-linear, right? So which is also connected to degree of the differential equation. So whatever the differential equations that we are going to study are degree 1 ordinary differential equations. So degree 1, what I mean by degree 1, there will be any power or any derivative you take, any function or any derivative of that particular function you take, it will be of power 1. So there will not be any squares or cubes coming into the picture. So here also you can see general form f prime of x has power 1, f of x also has power 1, and if you have f double prime or f triple prime in the differential equation, their power should also be 1 in order to be called as linear ODE. But if you see something like n of t whole square or n prime of t whole square, or its function is getting powered, or function's derivatives are getting powered, such a differential equation is not linear, it is non-linear. So there is some population model which is discussed in the lecture. You can have a look at it. So that population model is governed by this particular differential equation. And if you look at this expression, you will be observing that there will be n of t getting multiplied with n of t, which forms n of t whole square. Therefore, the degree of this differential equation will be 2. Right? So just like polynomials, how we had degree, here also the same way. Okay, so for a linear ODE, the degree is 1. For a non-linear ODE, the degree is greater than 1. Okay, so that is sufficient, I guess. So we'll not be focusing on non-linear too much. We will be focusing only on linear ODEs. Okay, so that the things that we are going to discuss are also linear differential equations. Okay, so now that we understood how the differential equation looks, the next step that we are going to do is how to find the solution of the first order linear ODE, then we'll go to the second order. Okay, so any doubts so far? So if you have
No,
doubts, you
sir.
can raise your
No,
hands
sir.
and ask. Okay. Okay, so this is the differential equation written in the general form, right, which is f prime of x plus some function p of x getting multiplied to f of x, and we have q of x, right? So these are the only things that are there in our first order linear ODE. And we are going to solve this particular differential equation now by taking the very simple case where our p of x is 0. So that means if we don't have this term, all we have was f prime of x is equals to q of x, which is like this, right? So if we have expression like this, what we can do, we can take integral on both sides, right? So integrate. If you integrate f prime of x, we'll get f of x. And if you integrate q of x, you'll get antiderivative or the integral of q of x, which is the antiderivative, right? So which will be a q of x. And since we are doing the integral, we'll have some integral constant. So you can take that constant on both sides. But if you have constant on both sides, you can bring the left hand side constant to the right hand side and make it as a single constant. Okay, so there is no point of writing f of x plus c1 is equals to a q of x plus c2, some other constant, because it is just an integral constant, nothing to, so it doesn't provide anything more to the solution. Okay, so therefore, easy case like p of x being 0, if you just do integral on both sides, we will get to the solution, right? So a simple example would be something like this. So f prime of x is sine omega naught t. If it is like this, you integrate, sorry, it should be f prime of t is sine omega naught t. Okay, so the variable is t. Okay, so f prime of t is equals to sine omega naught t. All we have to do is integrate on both sides. F prime of t will become f of t. And then since I am integrating sine omega naught t, we all know the integral of sine omega naught t is minus cos omega naught t divided by omega naught plus some constant c, as simple as that. So, okay, so easy case like p of x being 0 is very easy. What if p of x is some constant, right? So some constant which is independent of x. So p of x is some p. Now the equation will look like this: f prime of x plus p f of x is equals to q of x. Right, so once we have expression like this, what we will do is we'll try to eliminate this f of x or try to convert to the easy case. How we can convert to the easy case? We will try multiplying both sides of the equation by e power px. So if we have the constant as p, we will take that constant in the power of exponential e power px. We will multiply it on both sides. What will we get by multiplying it? We will see now. So we will have expression like e power px multiplied to f prime of x. Then we have pf of x and e power px will get multiplied to this. And on the right hand side, we will have e power px into q of x. Okay, so right hand side, you keep it aside for now. Look at the expression on the left hand side. So there is e power px, f prime of x, p into e power px, f of x. So now it is in the form of u of x into u prime v prime of x plus u prime of x into v of x. Right, so you just see like when you take v of x to be f of x and u of x to be p e power px, you can clearly see that it is in the form of u of x into v prime of x plus u prime of x into v of x. And this we know it's a standard product rule of our derivative, right? So if I am derivating u of x into v of x whole derivative, it will be u of x into, you take the first function, multiply it with the derivative of the second function plus take the first function's derivative times the second function, right? So Using that property, this e power px into f prime of x plus p into e power px into f of x will simply be u of x is e power px and v of x is f of x. So e power px into f of x derivative on the left hand side. On the right hand side, we have e power px into q of x. And this is like, now e power px into f of x, you treat it as some g of x. Right, so all we have is g of x derivative on the left hand side, and right hand side we have some function of x, which falls under the easy case. All we have to do is integrate on both sides. When you integrate on both sides, right, so when you integrate on both sides, what we'll get, left hand side will be e power px into f of x. Right hand side will be integral of this, which is the antiderivative of this. So a into e power px, so it is written like this, right? So e power px q is a function now. E power px q of x plus c. And if you push that e power px to the right hand side, the expression will be f of x is equals to e power minus px antiderivative of e power px q plus c into e power minus px. That's it. All we have to find is the antiderivative of e power px into q of x. So once we find that antiderivative, we can substitute it here, and that will be the solution to our given differential equation. That's it. And if you closely observe, we have this constant c in the picture, right? And we can eliminate this constant c or find the value of c using the initial conditions. Okay, so that I think we'll come to that by solving this falling object example. Okay, so we have this falling object example where our p of x is a constant, right? So this is the p of x, p of t, which is k by m, which is independent of t, right? So that is a constant, which is k by m, that p is k by m, and q of t is also a constant here in this case. So it was just g, right? If you remember, all we need was antiderivative of, so this is what we need basically for the solution. Antiderivative of e power px into q of x. So e power pt into q of t here will be e power p is k by m. So e power k by m of t and q of t is g, and we need the antiderivative of this. So if you closely observe, if I integrate this, so integral of e power kt by m into g dt, right? So you can pull out g, and integral of e power kt by m is nothing but e power kt by m whole divided by k by m, and there is outside g plus some constant c, right? So we are ignoring for now, and this m goes to the numerator and it will just be mg by k into e power kt by m. So that will be the antiderivative. That is what given here, right? So once we have this antiderivative, all we have to do is to substitute it, right? So we have the solution to be e power minus, right? So p is k by m. So e power minus k by m of t, right? I will write it here. So our v of t is e power minus k by m of t into this antiderivative, which is mg by k into e power kt by m plus c into e power minus kt by m. Now if you observe, this and this both will get cancelled, right? So e power minus kt by m plus kt by m will become 0, e power 0 is 1. So they both get cancelled with each other in the powers, and we'll have e power 0 and which is 1. So the expression that is left is mg by k. So mg by k plus c into e power minus kt by m. So still we have to find this c. So for that what we are going to use is this initial condition. So this initial condition that we know that at time 0 there is no speed. So speed of the object is 0 at t is equals to 0, which is v of 0 is equals to 0. So what we do, we will substitute that in this equation. We'll substitute 0 in this equation. Once we substitute 0, we'll have v of 0 on the left hand side and mg by k plus c into e power 0. Right, so when you substitute 0 here, the e power 0, which will be 0. So mg by k plus c is v of 0 and v of 0 is 0. So we'll put 0 and solve for c. C will be minus mg by k. So we'll bring that c and substitute here. If we substitute that minus mg by k and pull out, now you can see that mg by k and minus mg by k, you can pull out mg by k common and you will have 1 minus e power minus kt by m. So k and m are known to us. As mentioned earlier, k, m are known or given. So now if you see k, m, g also, g is also known to us. So when you substitute those values, you will see that v of t will be only in terms of t. Right, and this will be the solution. This is the solution. Solution to our ODE, first order ODE. Okay, so here also we did compute the antiderivative of e power pt q of t. Right, so that's the only challenge that we have here. Alright, so then we can plot this expression. Right, so v of t mg by k into 1 minus e power minus t by m by k. So it is written slightly different. It is minus kt by m is written like minus t by m by k. And this m by k is like time constant. It is called time constant. So we'll see this, how this voltage is being, how the speed is being changed in a particular intervals of times. Right, so m by k, 2m by k, 3m by k, 4m by k, 5m by k, like. And we'll see, you can also see that the speed has some limit. So it will not go beyond a certain value. Right, as time goes to infinity also, speed will not go to infinite. Speed is converging to some value which we call as v infinity. Like even if you drop from very maybe from sky, where that object can fall to the infinite distance, even if you drop like that, ball will not gain infinity speed. It will just gain a certain maximum speed and it will stay like that. And that maximum speed we can find by substituting t is equals to infinity in the equation, which is referred to as v infinity. So when you substitute infinity here, e power minus infinite, we know it is 0. So we'll have mg by k to be the maximum speed that any object, any falling object can attain. Right? It cannot attain more than that. So which is v infinity, and that will be attained at time infinite. And then we can also look at how much speed it has gained within one time constant, within two time constants, within three time constants, and so on. So within one time constant, it will reach 63% of its maximum speed that it can attain. So within the first time constant itself, it will attain some 63% of the maximum speed that it can attain. In the second time constant, by the second time constant arrives, it will reach 86% of its maximum speed. And all these things that we can get by substituting t is equal, m by k is equals to 1, m by k is equals to 2, and so on. Right, so here you can substitute. Yeah, 1 by m by k it should be. Right, so here e power minus, sorry. So this is e power minus 1 divided by m by k, and we'll take m by k to be 1. And then e power at t is equals to 2, it will be e power minus 2 divided by m by k. At time t 3, 4 and so on, we'll have this values. Okay, so at time t is equals to m by k, we'll have m by k divided by m by k, which will give us e power minus 1. At time 2m by k, m by k will get cancelled out, it will be e power minus 2. Like that. So 3m by k, at time 3m by k, m by k will cancel out, we'll have e power minus 3. So v infinity times 1 minus e power minus 3 is nothing but 0.95. So within 3 time constants, it will attain the 95% of its maximum speed. Then it will slowly reach v infinity. And if you plot, this is how the plot looks for velocity. Alright, any doubts in this plot? So plotting is also little important. So that is why I spent some time here. Any issues with the plot?
No, sir.
No? Okay, great. So we'll also solve quickly this RC circuit with DC source, that the second example that we have discussed. We have this equation. So in that equation also we have the P of X to be constant, which is 1 by RC. So R and C is given to us. So 1 by RC will be a constant and Q of T will be 0. So e power Pt Q of T will be 0 and antiderivative of e power Pt Q of T will be 0 because integral of 0 is 0. So if that is 0, then this expression, so I of t will be e power minus pt into antiderivative of ept e power pt q of t plus c into e power minus pt, right? So this is 0. So this term will become 0, will vanish. And all we left with is c times e power minus pt. And p we know is 1 by rc. Therefore, I of t will be c into e power minus t by rc. And we also gave the initial condition, right? So initial condition could be 0 or initial condition could be given as which is the current passing through that resistor, right? So I of 0 will be v by r. So v is equals to IR and I will be v by r and I of 0 is 5 by r. So from there you can substitute t is equals to 0. We will see that I of 0 is c and c, which is 5 by r, and therefore I of t will be 5 by r e power minus t by rc. So here also rc will be given to us, right? So these two things will be given to us and I of t will be only in terms of t. And even this also we can plot. Y of t is equals to 5 by r e power minus t by rc. And yeah, here the time constant that we are going to consider is rc. So anything divided by, so anything t by something will be taken as the time constant, right? So my and that is here it will be rc, and initially the current passing will be 5 by r, and then slowly it will deteriorate as time progresses. The current passing will go to 0, right? And also you can, in the first time constant, all you have to do is you substitute t is equals to rc, you'll have 5 by r into e power minus 1, right? So it will be 5 by r into e power minus 1. 5 by r is I of 0, right? So which will be I of 0 into e power minus 1, which will be 37%. So it will drop by 63%. So like that, it will drop by 87% within the next within two time constants, and it will drop by 95% within three time constants, and then it will slowly drop to zero. Okay, so this is like something inverse to what we saw previously, right? So previous graph was increasing, this was decreasing. All right, so any doubts here? So these are some examples on first order linear ODE. Okay, good. And now we are going to see second order linear ODEs with constant coefficients. So even in the second order linear ODEs, we are not going to see functions getting multiplied to the derivatives or the function. Rather, we will be seeing all the coefficients that you are going to see in the differential equation are just constants. Okay, and some real life example is this RLC circuit. Right, so you have resistor, conductor, and inductor. So all three, and we have a source voltage, and using the KVL laws, voltage across all three components, sum should be equals to the source voltage, right? So VR of t plus VL of t plus VC of t should be equals to VS of t. Then we know VR of t is Ri of t, VL of t is L into I prime of t, and I of t is C into VC prime of t. Right, so then you differentiate the first equation. We'll have V prime L of t, V prime R of t, V prime C of t is equals to Vs prime of t. So then V prime of L of t, you derivate this expression. For V prime R of t, you derivate this expression. And Vc prime of t is already available, which is 1 by Ci of t. And this is Ri of t, Ri prime of t. And only this expression will get added. Apart, so if you compare it with RC circuit, this expression is added, and that is L into I double prime of t. Right, so that will come here, and you divide the whole expression by L. You will have I double prime of t plus R by L, I prime of t plus 1 by LC into I of t plus is equals to 1 by L into Vs prime of t. Right, so that will be the second order ODE, because the highest derivative that is present in this particular differential equation is 2. Second derivative we have. So that will be the second order ODE. And if you see the coefficients, all the coefficients are just constants. So we don't have any functions coming into the picture. So this is a second order ODE, and it is a linear ODE with constant coefficients. Okay, and we have two cases here. One is when the source voltage is just constant, which is DC circuit, and if the source voltage is alternating, right? So which is alternating current, which changes with respect to time, which can be A sin omega t or A cos omega t, right? So two cases, and we'll see how to solve these kind of ODEs. Okay, and this is the general expression for second order linear ODEs with constant coefficients. So there will be three coefficients A, B, C. All three are for one for second derivative, one for first derivative, and one for f of x. And on the right hand side, you will have some function q of x. Okay, so A, B, C, q of x will be given to us, and we have to find f of x. So for solving this second order ODEs, we sometimes we have structured solutions. Sometimes we have to do some guessings. Okay, so that guessings and all comes with experience. And so for that we need to solve more and more problems. Then we'll know how to guess the solution, right? So there are some methods also, but mostly guessing is needed for solving second order ODEs. So we'll also see that. Um, but before that, we'll start with easy cases and then we'll build from easy cases. Okay, so when Q of X is 0, which is like if right side part is 0 in your equation, then it's called homogeneous linear ODE, second order linear ODE. Okay, so when Q of X is 0, our expression will look like A f double prime of X plus B f prime of X plus C f of X is equals to 0. So if this is how the second order ODE is present, then our life is little easier. What we can do is we can guess our solution to be e power sx, some exponential function. Okay, so e power sx is the solution. So once we guess the solution to be like this, and this will work when the right side part is 0. Okay, so when f of x is e power sx, we can find f prime of x, which is s into e power sx. We can also find f double prime of x, which will be s into e power sx, which will be s square e power sx. Right, so once we have these three things, f of x, f prime of x, and f double prime of x, we'll substitute it. Right, so where s is also some constant for now. So we will find that, but we'll assume that s is some constant. Okay, when you substitute it, you can clearly see a times s square into e power sx. Right, so a times s square into e power sx. So a times s square into e power sx plus b times f prime of x is s into e power sx plus c times e power sx is equals to 0. So all three terms in the left hand side has e power sx. You can pull that e power sx common. Once you pull that out, you will have as square plus bs plus c into e power sx. That should be equals to 0. So now we know we have studied exponential functions. E power sx can never be 0, right? Even though x tends to minus infinite, it approaches to 0, but not exactly 0. Since e power sx is not 0, what should be? So we have product of two things and that should be equals to 0, and one is not 0, which implies that the other one should be 0. Right, so this should be 0, which is as square plus bs plus c should be 0, which forms a quadratic equation in terms of s. Right, so abc is given to us. We should find s. So we will pick s such that as square plus bs plus c is equals to 0, which is a quadratic equation, and we can solve the quadratic equation and we can find s. Right, so we have standard formula also. We can use it: minus b plus or minus 4b square minus 4ac divided by 2a. Right, so this will be s, and for these s's, e power sx is a solution. And if you clearly see, there are two possible s's, maybe one. It depends on how many roots this quadratic equation has. And this so formed expression is called the characteristic equation. Characteristic. Okay, so this is called as characteristic equation, and we will solve this characteristic equation and for s, and once we have s, then e power sx will be the solution. Right, and as I said, this quadratic equation can have distinct real roots, or it can have the same real root repeated twice, or it can have no real roots, maybe it can have complex roots, right? So we have seen those also. So these are the only three possibilities for quadratic equation, right? So either two real roots or repeated real root, or there are no real roots. The two roots obtained were just the complex roots, and those complex roots will be complex conjugates to each other. These are the only three possible cases. We'll see case by case. If the characteristic equation has two distinct real roots, say S1 and S2. Okay, so once you find the roots, let S1 and S2 are the two roots. Right, so now e power S1x and e power S2x both will be the solutions. Right, so because both S1 and S2 satisfies this as square plus bs plus c is equals to 0, and S1 and S2 are not equal. So these are two solutions. So once we have these two, then any linear combination of these two will also be a solution. So if f1x and f2x are solutions for some differential equation, then c f1x plus c1 f1x plus c2 f2x are also solutions, right? So you can prove this very easily. You take the linear combination. I think it's an interesting thing to do. So e power s1x and e power s2x are solutions to this ODE, a f double prime of x plus b f prime of x plus c f of x is equals to 0. So now we have some other solution, right? So let's say some L of x, which is c1 e power s1x plus c2 e power s2x. So my claim is even L of x will also be a solution. That means if I substitute this function in this expression as f of x, it should get satisfied. Right? So in other words, instead of using L of x, I claim that this f of x will be the linear combination of these two solutions. And we can prove that by checking. Right? So you take the derivative of f of x, you will have c1 s1 e power s1x plus c2 s2 into e power s2x. Then you take double derivative also. You will have c1 s1 square e power s1x plus c2 s2 square into e power s2x. So all we have to do is to substitute. So we substitute all these three here, right? So if you substitute, we'll have a into this f double prime of x will be c1 s1 square e power s1x plus c2 s2 square e power s2x plus b into f prime of x will be c1 s1 into e power s1x plus c2 s2 into e power s2x plus c times f of x is c1 e power s1x plus c2 e power s2x, which will be equals to 0. It should be equals to 0. So we'll check whether the left hand side that we are getting is 0 or not. So now we will pull all e power s1 terms together and e power s2 terms together. So e power s1 terms are this one, and this one. Right, so if I pull all these three together, we'll have a c1 s1 square plus b c1 s1 plus c into c1 whole into e power s1x. Plus, if I pull all e power s2 together, we'll have a into c2 into s2 square plus b into c2 into s2 plus c into C2 e power s2x is equals to, should be equals to 0. So we'll see whether left hand side is being equals to 0 or not. So you pull out C1 common from this, you pull out C2 common from this. So we have C2 also common, C1 also common. If you pull that out, we'll have a s1 square plus b s1 plus c whole into c1 e power s1x plus a s2 square plus b s2 plus c into c2 e power s2x is equals to 0. So if you carefully look at the left hand side expressions, we have two terms, right? So one is this term and another one is this term. Both the terms are zeros. And why are they zeros? If you just go back a bit, if S1 and S2 are roots of this equation, what does it mean? If I substitute S1 or S2, it will satisfy, right? So that means A S1 square plus B S1 plus C will give me 0, as well as A S2 square plus B S2 plus C is equals to 0, right? So it should be true because only then S1 and S2 will be the roots, or else it won't be the roots. So when they said S1 and S2 are the roots, that means those should satisfy the equation. So that means if I substitute, the equations get satisfied. So we have these two equations, and if you look at here, as1 square plus bs1 plus c is nothing but 0 because s1 is a root. as2 square plus bs2 plus c will also be 0 because s2 is a root. Right, so which implies that 0 is equals to 0. That means the expression that we took for f of x is a solution to the given homogeneous equation, differential equation. So that's the proof for this. So we'll write the general solution instead of mentioning it as e power s1x and e power s2x. We'll take the linear combination of it, and hence the general solution for the second order homogeneous differential equation, where our characteristic equation has distinct real roots s1 and s2. Then the general solution will be in the form of f of x is equals to c1, some constant c1 times e power s1x plus some constant c2 into e power s2x. S1 and S2 we can find from solving the characteristic equation, and we are yet to find c1 and c2. So for that, we will be given some initial conditions, right? So some initial conditions like function value at a certain point and the first derivative value at a certain point, x naught. Okay, so these things will be given to get C1 and C2. Right, so when we solve the example, we will see. So here is the example where the second order homogeneous differential equation is given to us with some initial conditions f of 0 and f prime of 0 to be equals to 1. Both are equals to 1. Right, so if you form the characteristic equation from this, so how do we form the characteristic equation? We will assume that so we will assume the solution to be e power sx, right? So if it is e power sx, from that we will get f prime of x to be s into e power sx, f double prime to be s square into e power sx, right? Then if I substitute them, I'll have s square into e power sx minus 6 into s into e power sx plus 8 into e power sx is equals to 0. Then pull out e power sx common and you remove that e power sx because e power sx will never be 0. So whatever is remained, that should be equals to 0. Right. So if I pull out, I'll have s square minus 6s plus 8 into e power sx to be 0, which implies that s square minus 6s plus 8 to be 0. That is what our characteristic equation is. So if you ask me, should I do all these things to get to this? The answer is no. All you can do is, in place of f double prime of x, if you have the second derivative, you should replace it with s square, the second power. And if you have the first derivative, you replace it with s. If you have f of x, you don't, it's a constant thing. Okay, so like that. So f of x, you replace it with 1. F prime of x with s. F double prime of x with s square, and so on. So if you have f triple prime of x, you will replace it with s cube. Okay, you will not have, but just to let you know that. So the derivatives power, so the derivatives will be replaced with s power, the derivative. Okay, so you can get this expression. Now s square minus 6s plus 8 is equals to 0 is a quadratic equation. When you solve it, you will get that s can be 2 or s can be 4. So these are the s1 and s2. So this is s1 and this will be s2. So now the general solution that we have seen is c1 into e power s1x. Here s1 is 2. So c1 into e power 2x plus c2 into e power 4x. And we are yet to find c1 and c2. For that we'll take the help of this initial conditions. So if you substitute 0 in this general solution, we'll have f of 0 to be c1 plus c2 and f of 0 is given to be 1. So c1 plus c2 should be 1. And when you take the derivative of this general solution, derivative on both sides, you'll have f prime of x, right? So to get to this, there is an intermediate step. You take the derivative, f prime of x will be equals to 2c1 e power 2x plus 4c2 e power 4x. Now substitute x is equals to 0. You will see that 2c1 plus 4c2 should be equals to f prime of 0, which is 1. So we have two equations now with two variables, right? So we know how to solve it. So solving this system of linear equations, we'll get c1 and c2 and substitute that c1 and c2 in the general solution. And you'll get the solution to be f of x is equals to 3 by 2 e power 2x minus half e power 4x. So this will be the solution to the given second order homogeneous differential equation with constant coefficients along with initial conditions. Okay, so this is how we solve. Okay, is this okay?
Yes, sir.
Okay, nice. So what if we have repeated real roots, right? So where there are no s1 and s2 now, whatever the quadratic equation that we have has only one real root. And if you just recall the concepts of quadratic equations, when can we have exactly one real root? So when the quadratic function exactly touches the x-axis only at one place, right? So if it is touching at only at one place, if it is touching like this and going, then the so formed quadratic equation will have only one real root, and that is this, right? So something like this. And why I said this, because not only a s1 square plus b s1 plus c is equals to 0, you should also observe that the axis of symmetry will also be the root, So if I find s1, this s1 will be minus b by 2a, right? So just recall. So if this has only one real root, that means the left hand side is a perfect square, right? So if it is a perfect square, then we'll have symmetriness for our quadratic function exactly at the root value, right? So from here you can clearly see 2a s1 plus b will also be 0, right? So these two things are used to prove that this will be the general solution. Okay, so the solution of this quadratic equation will have only one real value, which is S1. So therefore the solution that we have is e power S1x. We will not have e power S2x anymore. We have only e power S1x. But even though we have e power S1x, then x into e power S1x will also be another solution. So if x into e power S1x is also another solution, then e power S1x and x into e power S1x linear combination will be the general solution. Right? So the general solution will take this form now. Instead of C1 into e power S1x plus C2 into e power S2x, we will have C2 into x into e power S1x. It will be slightly different. And we can again prove this. So I have written it. If you want to prove how x into e power S1x will be a solution, if S1x, e power S1x is a solution, then we'll try to prove it. F of x is equals to x into e power S1x. Then f prime of x will be, this is the product function, right? So x is one function, e power S1x is another function. We'll have x into e power S1 into e power, x into S1 into e power S1x plus the derivative of x is 1 into e power S1x. And when you take the double derivative, all you have to do is take the derivative of this. So if I take the derivative of this, again, this is the product of two functions, x and S1 into e power S1x. So it will be x into S1 s square into e power S1x plus 1 into S1 into e power S1x. Then the derivative of e power S1x, which will be S1 into e power S1x. So these two will get added up. We'll have x into S1 square into e power S1x plus 2 into S1 into e power S1x. Right, so this will be the expression for f double prime of x. This will be the expression for f prime of x, and this is for f of x. When you substitute, so we have to substitute in this equation, right? So when I substitute a into f double prime of x, so a into these two terms, so a into S1, a into S1 square x e power S1x plus 2a into S1 into e power S1x. So these two things are for this term. And then b into f prime of x. So b getting multiplied here. So we'll have b into S1 into x e power S1x plus b into e power S1x plus c into x into e power S1x. That should be equals to 0. Now if I pull all this x into e power S1x terms separately and e power S1x terms separately, I will have, so this is x into e power S1x, x into e power S1x, x into e power S1x. So the coefficients are a S1 square x, sorry, not x, a S1 square and b S1 and c. Right, so other terms, if I club together, I'll have 2a S1 and b. Right, so if I pull them separately, I'll have as1 square plus bs1 plus c into x into e power s1 x plus 2as1 plus b into e power s1 x is equals to 0. So when, as mentioned above, when there is only one real root for the quadratic equation and that real root is s1, not only this will be 0, this will also be 0. Because the formed quadratic function will exactly touch x-axis at the root, right, which is also the axis of symmetry. So since these two are becoming zeros, implies that 0 is equals to 0, so satisfied, right? So the function f of x is a solution. That means x into e power s1x is a solution. So once these two are solutions, its linear combination will also be a solution. That's it. So if it is repeated real root, the general solution will take slightly different form compared to the repeated real root. Okay. And finally, okay. So there is also an example. So we have this ODE given to us with some initial conditions. Then if you form the characteristic equation, it will look like this, right? So f double prime of x, you replace it with s square minus 6s plus 9 is equals to 0. If you solve the quadratic equation, you will see that you will have the two real roots that you are going to get are the same and they are equals to 3. Right, so then the general solution will be of the form c1 into e power 3x plus c2 into x into e power 3x. Then if I substitute x is equals to 0, I will no longer have this term because there is x here. When I substitute 0, this will be gone and I will have only c1. So f of 0 will be c1, which is 1. So c1 will be 1. And if I take the derivative of this, f prime of x, which will be 3c1 into e power 3x plus c2 into 3x into e power 3x. So you have to take the derivative of e power 3x first, then plus we'll have one more term c2 into derivative of x is 1, so e power 3x. Right, so when I substitute x is equals to 0, this term will vanish. This term will go to 0 when x is equals to 0. So all we are left with is 3c1 plus c2, that should be equals to 1. So since we have c1 to be 1, if you substitute here, you will get c2 to be minus 2. So substituting c1 and c2 values, you will get e power 3x minus 2 times x into e power 3x. You can pull out e power 3x common, then you will have 1 minus 2x into e power 3x. That's it. So this is how the solution is obtained. Okay. Alright, then comes the third case when the roots are complex conjugates to each other. Right, so S can be some r plus it and r minus it. So S1 is r plus it, S2 is r minus it. And the solutions are e power S1t and e power S2t. So if I just substitute them, so this is e power st, sx, sorry. Right, so e power sx. Then if I just substitute s is equals to r plus it, then we'll have e power rx plus e power itx. So e power itx using the Euler's formula, we'll have cos tx plus I sin tx. Right, so if you substitute that, we'll have e power rx into cos tx plus I into e power rx into sin tx. And similarly, e power rx into e power minus itx, the other solution is e power rx into cos tx minus I into e power rx into sin tx. And these are both are just the linear combinations of e power rx cos t and e power rx sin tx. Right, so therefore, the general solution for this looks like e power rx into c1 into cos tx plus c2 into sin tx. And again, you can also prove this. You can take this and take the derivative, double derivative, and substitute it and see that this will also be the solution. Okay, so then what we have is finding c1 and c2, and we can again do that by taking the help of initial conditions and we can find it. Here is example for that. Given the differential equation, form the characteristic equation, then get the roots. Once you got the roots, you have to identify what is r and what is t. R is 5 by 2, t is root 7 by 2. Right, so the general solution will be e power rx, which is e power 5x by 2 into c1 into cos tx, t is root 7 by 2, so cos root 7x by 2 plus c2 into sin root 7x by 2. Then using the initial conditions, you can find c1 and c2. If you solve it, you will get c1 to be 1 and c2 to be minus 3 by root 7. If you substitute, you will get the solution. Right? So this is how you can solve homogeneous second order linear ordinary differential equation. Right? So if you have non-homogeneous case, where non-homogeneous is the right side part is not 0, it is some other function q of x. Okay, so if it is not 0, what we'll do is we'll get to the solution in 2 steps. One, we will find the solution for this non-homogeneous case by having q of x as it is, which we call it as g of x as the solution. And we'll also find the solution for the homogeneous case, which is when a f double prime of x plus b f prime of x plus c into f of x is equals to 0. Then the sum of these two, which is the solution for homogeneous equation and the solution for non-homogeneous case, which is also called as particular solution, right? So the addition of these two gives us the complete solution. So the complete solution is the sum of homogeneous solution plus the particular solution, and we will try to solve this particular solution using guesswork only. Okay, so there are no standard methods, but for particular solution, all we can do is guessing. So if q of x is just a constant, our guess is that the function is a constant, the solution is a constant value. If q of x is some combination of linear combination of sinusoids, u sin x plus v cos x, then our solution that we are going to guess will also be the linear combination of sin x and cos x. Right, so that is how we guess. Right, so you can see some examples also. If q of x is some 4, right, so q of x is 4, then we guess that f of x is some e. If f of x is e, then f prime of x is 0, f double prime of x is also 0 because derivative of a constant is 0. So all we are left with is 5e is equals to 4. So from there e is 4 by 5. So you can clearly see that f of x is 4 by 5 is a solution, is the particular solution. Okay, and then we'll solve for the homogeneous case also by replacing q of x by 0. You'll solve that. You'll get the you'll get the homogeneous solution. You will add this 4 by 5 to that homogeneous solution. Okay, which will give the complete solution. Right, you can clearly check f of x is equals to 4 by 5 is a solution for this differential equation. Right, so this is the particular solution that we are going to get. So similarly, if you for q of x is some sin x or cos x or any linear combinations, since we guess that our solution is r sin x plus s cos x, you take the derivative of this, double derivative of this. We know how to take the derivatives of cos and sin. Then you will see that f double prime will be minus r sin x minus s cos x. F prime will be r cos x minus s sin x. And then f of x is r sin x plus s cos x should be equals to sin x. Then on the left hand side, you will see some coefficient for sin x and some coefficient for cos x. On the right hand side, we didn't have any cos x terms. So the left hand side coefficient should also be 0. Coefficient of cos x should also be 0. So the left hand side coefficient is minus s plus minus 2s plus 5s. Sorry, minus s plus 2r and 5s, which is 4s plus 2r is the coefficient for cos x on the left hand side. And on the right hand side, the coefficient is 0 for cos x. So 2r plus 4s should be 0. Similarly, we compare the coefficients of sin x on the left hand side and the right hand side. Right hand side, we have the coefficient to be 1. And on the left hand side, you will see that minus r minus 2s plus 5r, which gives us 4r minus 2s should be equals to 1. And we'll solve for r and s here. Right, so two equations, two variables, we know how to solve it. Get the values of r and s. Then those are the coefficients of sin x and cos x in the solution. And if you substitute it, we'll get this. And this is the particular solution. This is not the complete solution. For complete solution, again, what we have to do is replace sin x by 0, which is like homogeneous case. You solve the homogeneous case and get the solution for the homogeneous case and add this to that homogeneous case, which will be the complete solution. Okay. All right. So I think that's all for today. So there are a couple of concepts also dealt at the end, which is like more involved with circuits. So something related to overdam, under dam. So we have solved uh, some non-homogeneous cases, complex cases. Okay, so there we will be coming in. We will be forming equations, second order equations, heavily loaded. Okay, so you can go through it, but since week 12 is released very near to the exam, with respect to examination point of view, we will not be asking that complicated stuff, but that is also important to learn and which will help you in the next courses. But as far as math 1 concerned, that is like an extra additional content that you can think of. Okay, but if you have any doubts related to that, we have again a session after the deadline, right? So in that you can ask related to that. But as far as examination point of view, you should know how to solve. The first order linear ODE, right? So the standard form, general form, you should know how to solve it, and then the homogeneous case of second order, and then at least with the constant coefficients, given q of x to be some constant or some combinations of sinusoids. Okay, so these things are sufficient. Whatever I discussed today, those are sufficient and solve more and more problems related to this with respect to examination point of view. Okay, but the last two lectures of week 12 is also quite important in your next coming courses. You can go through that. All right, so I will upload that. I think week 12 PA and I think lecture slides has been uploaded, right? So I have asked them to upload and I think they have uploaded it. Only the solution part of PA is pending. So we'll upload it. All right, so with that, I'm done. If you have anything to discuss, we can discuss, or else we can formally close the session here so that the rest 25 minutes we can use it for some other better thing. Okay, so then we'll meet during the revision sessions. So even during the revision sessions also, we'll just go through the same thing. Once again, we'll solve more problems rather than theory. Okay, so we'll do week 11, week 12 together by solving more and more problems. All right, guys. So that's all for today. Thanks all for joining and have a great day. Bye.